Hello, everyone, and welcome back to the YouTube channel, An American Professor. We're going to pick up where we left off last time on this lecture series on the basics of reinforcement learning. So far in the series, I've covered what states are and what controls are in regards to a reinforcement learning problem. In this video, I'll be covering the important topic of rewards in reinforcement learning and talking about the different characteristics of rewards and reinforcement learning. So without further ado, let's get to it. Refer to these articles to see content I've already discussed, such as a general introduction to RL, the importance of states in RL, and controls in RL. In this article, I overview what rewards are in RL. I also explain the many characteristics of rewards in RL and how those distinctions can impact modeling, the modeling of the problem and affect agent learning. And now I describe why rewards, and in particular the reward function, is an important modeling component for any RL problem. Here you can see Pac-Man arcade video game. Video games are really good environments and common environments for testing different RL algorithms, but they're quite simplistic. But the optimal policy can often elude us, game players. But AIs are very good at finding the optimal policy in any game. And we've seen that over and over. Just if you want an example, look up the Go playing RL agent that I think DeepMind developed to beat the world Go champion. But I digress. So anyway, what types of rewards are there in RL? In reinforcement learning, rewards are a key part of the learning process. Rewards signal to an agent what controls it has taken that are valuable, indicating which one should be repeated when the same state is visited by the agent in the future. There are three main types of rewards: extrinsic, intrinsic, and shaped rewards. These are more psychological terms, but I like the terminology. Extrinsic rewards are externally provided rewards such as money, points, or something else that is valuable. Intrinsic rewards are generated by the agents themselves. Think of motivation from psychological perspective, based on their internal state and their own model of the environment. Shaped rewards are a combination of extrinsic and intrinsic rewards that have been designed to encourage a specific kind of behavior. These distinctions come from the field of psychology, but have a role to play in RL problems too. I'll mainly be discussing intrinsic rewards because that's typically what RL engineers build, is they have an agent that has a model of the environment and it knows what states are possible and what controls are possible, but it needs to discover, based on the reward function, what is the optimal thing to do in each state. Rewards play a critical role in RL by providing a motivation for agents to learn and explore. Without rewards, agents would have no way of knowing which controls are important and would be unlikely to make any progress in completing its assigned task or solve a certain control problem. Rewards provide feedback to the agent, allowing it to learn from its controls and adapt its behavior over time. Furthermore, as is discussed in this article, rewards can be either frequent or sparse, and deterministic or stochastic. So frequent versus sparse rewards in RL. Frequent rewards are any non-zero rewards an agent receives during every stage of the decision problem. This could be for a finite horizon or an infinite horizon problem setup. On the other hand, sparse rewards are infrequent, as the name implies. Sparse rewards could be given only after some number of steps, say when an agent wins a game or completes a desired task. So it's much harder to learn under sparse rewards than frequent rewards. Next, characteristic of deterministic versus stochastic rewards in RL. There are two main types of rewards in RL: deterministic rewards and stochastic rewards. Deterministic rewards are those rewards that always occur when an agent reaches a certain state and takes a certain control. Mathematically, if the agent is in state X and takes control U, it will always, I repeat, always receive the same reward R, hence the name deterministic reward. In the future, I will present more detailed mathematical descriptions of states, controls, and rewards, and we'll even do projects where you'll see the rewards being received in real time by an agent being trained in a simulation. But for now, I explain the RL material at a beginner's level. As an example that's illustrative, if we have a running robot that runs laps around a track and is rewarded the same amount of points for each lap it completes and nothing in between, then the reward is deterministic. And here we can say that the reward is sparse too. On the other hand, stochastic rewards are those that may or may not occur when a certain state is reached or a certain control is taken. For example, if the running robot has a 50% chance of receiving a point every time it completes a lap around the track, then the reward function is said to be stochastic. Stochastic rewards are a more general formulation than deterministic rewards. In games with stochastic rewards, generally more exploration is required on the part of the agent, and it takes longer for an agent to learn the optimal policy because the environment is doling out stochastic rewards instead of deterministic rewards. A bit on the notation or terminology of cost versus rewards and RL problems. In some books, papers, or tutorials, you may notice some authors use cost instead of rewards for their agents. This simply is a matter of optimization. If those authors frame their problem so that they are trying to minimize cost incurred rather than maximize rewards obtained, you will see cost instead of rewards in their works. So replace the letter R with the letter C as the optimization variable in your problem. Additionally, the max operator would be replaced everywhere by the min operator in the problem and algorithm descriptions. Some different reward function examples. In RL, the agent is rewarded for taking controls that lead to successful states. The rewards can be immediate, such as receiving a point for each step taken in the right direction, or they can be delayed, such as receiving a point at the end of the episode once the goal is reached. There are many different ways to define rewards, and the choice of reward function can have a substantial impact on the learning process. For example, rewards that are too small may not provide enough motivation for the agent to learn, while rewards that are too large may result in the agent taking too many risks. Finding the right balance of rewards is an important part of designing a successful RL algorithm. A rewards function is used to define what constitutes a successful or unsuccessful outcome for an agent. Different reward functions can be used depending on the goal of the agent. For example, if an agent is trying to maximize its score in a game, then a rewards function could give positive rewards for winning or getting closer to winning and negative rewards for losing, similarly getting closer to losing. On the other hand, if an agent is trying to reach a target location as quickly as possible, the rewards function could be the negative of the number of steps taken so far to encourage the agent to reach the goal in minimum time. Similarly, the reward function could take into account distance from the goal to where the agent currently is too as an inverse function. As an example, reward function using distance could be one where the reward decreases as a 1 over 1 plus d, where d defines the distance from the agent where the agent currently is relative to a goal location. In conclusion, there is no one absolutely correct rewards function for any given task an RL agent must solve. And different rewards functions can lead to different behaviors by the agent. It is important to carefully select a rewards function that will encourage the desired behavior from an agent. Oftentimes, a specific criterion is defined for optimization, and engineers look at the trained policy after the fact to discover what the agent has learned during testing. In this case, engineers often learn clever strategies for control from analyzing the trained agent's policy that the engineers never could have thought of or imagined before the training occurred. Or the new policy could be something that breaks with convention in some field. Though rewards can be used to shape behavior, there are several limitations to using rewards in a real learning system. First, rewards need to be given frequently in order for the behavior to be maintained. This can be impractical, especially if we're dealing with the real life practical setup rather than a simulation, say something involving tangible items like food, toys, or money. Second, rewards can inadvertently teach agents that they only need to perform a desired behavior when they are being rewarded. Third, rewards can create competition and conflict among agents rather than cooperation in a multi-agent setting. For these reasons, it is important to consider the limitations of rewards or reward functions when using them to shape agent behavior in a real setting. An alternative is to build a simulation of the real environment and train the agent in a simulator. This is cost effective. Finally, for any realistic agent implementation, I believe in a human in the loop to monitor or have some program checking the agent's behavior over time after training to verify it is operating in a safe or reliable manner while meeting its goals or desired objectives. Until next time, consider becoming a media member to never miss one of my stories and gain unlimited access to my writing and the writing of other authors by following this link and the link in the description. Hope you enjoyed the video. Don't forget to hit that like and subscribe button to stay up to date on my YouTube channel as well.